Hello, so in this video, I'll be reviewing a National Physics Olympiads second stage problem 1. So the first problem says, the helicopter is spinning its fans with omega angular velocity. The fan has length L, and the helicopter's mass is m. Prove the following equation using Bernoulli's equation. And we have the equation right here. Pi times rho times omega squared times L to the power of 4 divided by 4 has to be more or equal to mg. So for this problem, we first start with, of course, as stated here, Bernoulli's equation. What is Bernoulli's equation? To re-jog your memory, Bernoulli's equation is P1 plus rho g h1 plus rho v1 squared divided by 2 equals p2 plus rho g h2 plus rho v2 squared divided by 2. The rhos, or the density, may vary if you're actually going from water or going from one substance to another substance, but here the helicopter is going through from air to air, so the density won't really change. So how can you really picture this problem here? So basically, what we have here is mg. What's mg? Mg is the gravitational force that is pulling down the helicopter. And for the helicopter to fly up, it needs to overcome this force that's pulling it down. So we come to a conclusion that pi rho v omega squared L to the top power of 4 divided by 4 is actually some kind of force. But what kind of force is it? Since we're using Bernoulli's equation, this force has to be tangled with pressure. So this is most likely a force caused by pressure. If we were to jog our memory of the definition of pressure, pressure is force over some kind of area. Let's make this a little, very, very little amount of force over a very, very little amount of area. You'll see why later. So basically, the force we're talking about here is the force we're talking about here. So to find the force, we're going to have to find P, and we're going to have to find A. So to find P, we can find it from this equation, Bernoulli's equation. Well, how do we find P from Bernoulli's equation? Let's picture the problem. Well, let's draw the problem. Let's draw the helicopter. Let's say this is the helicopter body. Got its little legs here. And the big fan is right here. It's turning with omega angular velocity. There is downward force of mg, and the upward force has to overcome this mg for it to fly. So what we're going to picture here is air going through the bottom part of the helicopter and exiting through the top part of the helicopter. And since there is not much change of height here, so basically from here to here, do a little a different color. From here to here, and from here to here, there's really not much change. The height isn't really changing at all. So we can say that both rho GH1 and rho GH2 are way, way, way much less than 0.1. And then we can just have these two out of the equation so we can make it easier. Let's write it this way. P1 plus rho, B1 squared divided by 2 equals, okay, why is it divided by 2 equals, wow, it's bugging out. All right, anyways, P2 plus rho V2 squared divided by 2. All right, so the next thing we're going to do is define these two speeds. What exactly are these two speeds? So basically, V1 is the speed of this bottom part here. How fast is the air going through in this bottom part? And V2 is the top part here. How fast is the air exiting out through here? So since the bottom part doesn't really make any speed, V1 is equal to 0. And because there's a fan on top of the helicopter, V2 is going to be V omega times R. Let me say this again. There is no speed at the bottom part. No speed is being constructed on the bottom part. There's no speed on the bottom part. But on the top part, we have a fan. And this fan is basically the speed that's going to pull us up. So to say this again, there is no speed on the bottom part because there's nothing that's making speed. But there is speed on the top part because this fan over here is turning with omega angular velocity. And the relation between linear and angular velocity is V equals omega R. So V2 will have to equal to omega R. So let's plug in our newfound understandings into this equation. Since V1 is 0, this part is going to get scratched out. So that's just 0 plus 0 equals P2 plus rho. From what we have found here, V2 is now omega times R squared divided by 2. Now what do you do from here? There's two pressures. Over here, we were actually supposed to say the difference between pressures, delta P. So that will mean delta P is equal to dF divided by dA. So how can we get delta P? Delta P is the change or the difference between the pressures. So let's say delta P is P1 minus P2. And look, P1 is here, P2 is here. If we bring P2 over to this side, it'll be P1 minus P2 equals rho omega R squared divided by 2. That means delta P is equal to rho omega R squared divided by 2. Nice. We got rho omega R squared divided by 2, and that will equal 2 delta P. So we got the P part. The P part is down. Okay, so what's A? What's the area? The area is basically this circle that the fan is making while it's spinning. This circle. So what's the area of a circle? The area of a circle is pi r squared. So what's the very, very, very little amount of area? We can differentiate this. dA over dr. It'll equal to bring the 2 down, 2 pi r. So dA will equal to 2 pi r dr. Let's substitute this into here and bring our p into here as well. Also, multiply both sides by dA. So we get f on one part and pa on the other part. So df equals delta p dA. That's what we get. Since we know dA is 2 pi r dr, and since we know delta p, it's up here, we can find out df is equal to rho omega r squared divided by 2 times 2 pi r dr. All right. So to find the big force, we can just integrate this equation. So integrate df. This differential and this integration will cancel out, leaving f alone. So we get big F. Big F equals the integral of rho omega squared r squared divided by 2 times 2 pi r dr. Okay, what do we integrate over? Since the max amount of, so we're integrating length, since this is a dr right here. We're integrating length. What's the maximum amount of length that the fan could have? It's L, as stated above here. The fan has length L. So the most length it can have is L. So we integrate from 0 to L. Since rho, omega, and 2 pi are all constants, we can bring them out of the integral. So let's bring them out. Rho omega squared divided by 2 times 2 pi. Integral of 0 to L. You multiply r squared by r, you get r to the power of 3. R to the power of 3 dr. These two cancel. And r to the power of 3 integrated over r is r to the power of 4 divided by 4. So rho omega squared pi times r to the power of 4 divided by 4 over 0 L. And since this is 0, we just plug in L for r, and then we get rho omega squared pi L to the power of 4 divided by 4. And this will equal to a force that is going to act up from the helicopter and pull it up, basically. And just like that, we proved that this equation is correct. Since the upward pulling force has to be more than the downward force, mg, F has to be more than or equal to mg for the helicopter to actually fly up. And F here is just this monstrosity. And if you plug it in for this, we get rho omega squared pi L to the power of 4 divided by 4 has to be more or equal to mg. And just like that, we proved that this equation is valid.